Hello, everyone, and welcome. My name is Jamil Siddiqui, and I'm very excited to be here with you this evening. This is the first ever AP Calculus stream hosted by Fiveable, and you're all a part of it. And I'm, like I said, excited to be here with you tonight to talk to you a little bit about limits. I'm located here in Massachusetts. If you don't mind, if you guys could just kind of check in with me on the chat function and say hello, so I can see who I've got and how many people I've got out there, that'd be great. We're going to be talking tonight about graphical limits. So my first question I have for you all is how many of you have already gotten to limits in your classroom and they're studying limits? Could you give me some kind of feedback, or maybe a yes, we have, no, we haven't, thumbs up, thumbs down on the chat, so I can kind of see where you're at. In my class, we actually just started school last week, so we are pretty much at the beginning of the course. Depending on where you're in the country, maybe you've already started, maybe you haven't. I'm looking at the responses so far, and it seems like you guys are kind of in the same place my class is. You haven't started it yet, which is great, because it's exactly what we're going to be doing, is taking it from the beginning and showing you the basics of limits and then going forward with that. So let's see here. Let's go to our presentation this evening while we wait for everybody else to join us. All right, so graphical limits. What are they and how do we find them? That's what we're going to be looking at. My name is Jamil Siddiqui again, and I'm very excited to be bringing this to you. So here we go. If you want more information about Fiveable, please follow us at all the various social media, Twitter, we're at Instagram, YouTube. We're always posting what our new streams are going to be about, so you'll know when they're going to be posted and what topics we're going to be covering, so you can follow along with us. Tonight, we're going to be looking at the following. We're going to look at the definition of the limit so that you're familiar with what it is. We're going to be talking about the notation that we need mathematically to properly portray the limit. We're going to dive into the idea of a one-sided limit, and then how that leads us to understanding overall limits. So again, if you guys are giving me the feedback that most of you haven't gotten to this yet, we're going to take it from the beginning, and we're going to start from new. So the last thing we'll cover is our properties of limits. Up. Don't be shy. Okay, Haruko's got an answer for me. Great. Brendan, same. And as you guys are putting this in, you guys are doing exactly what my students did today. Okay, they looked at it and they just kind of common sensed it. They're like, all right, I might not be familiar with what this notation LIM means, but I certainly know x squared. I certainly understand that x is, and I've got this arrow, which means x is getting close to 3. So that answer should be 9, and it is. But what we really want to do is understand, what are we doing when we do this process? Because although getting the answer is nice, understanding the mathematics behind it is far more important. And I'd be willing to bet that most of us, when we got this answer, all we did was say, let's plug in 3 and let's square 3 and get 9. And although that led to the correct answer for this problem, that's really not what's happening with a limit. So let's go ahead and talk about how we read this notation if it's new to you. The way it's read is the limit of x squared as x approaches 3 is 9. You could also switch it around. You could say the limit as x approaches 3 of x squared is 9. Both of them are correct ways to say it. What I want you to pay attention to is that there are really 3 kind of parts to it. You've got the LIM, which signals that you're doing a limit. You've got the x squared, which is your function, and you've got the x goes to 3 part. Leave any one of these parts out and the limit doesn't make sense. So be sure that as you're writing limits and you're using limits, you're making sure you're filling all 3 of these parts. We'd like to talk about the definition of a limit right now. So if you don't mind, if you got a chance, why don't you just put something into the chat, make a guess if you haven't had it before, or if you do know a little bit something about it, feel free to put it in. And I'm just going to kind of gauge where we are at with your background knowledge. In mathematics, we use the word definition all the time. But really, the first place I came across it was my English class. We had our vocabulary words every week that we had to define. Definition in an English class, not a big deal. You get your dictionary, you look it up online, and you know what the word means. But when we're talking mathematics, what does it mean to be defined? So before we talk about the definition of a limit, I think it's important that we just say, what does it mean to be defined? So I'm going to ask you a really simple question. You're all familiar with the number 2, right? Everybody knows 2. There's no doubt in my mind that all of you are familiar with the number 2. But if I asked you to define 2, what would you write? What would be your definition? Put it into words. What do we mean by 2? So, feel free to try to put something in there. But when I ask my students this, I say, well, what's 2? Well, they all look at me and just hold up 2 fingers. This is what 2 is. But does that define what 2 means? So this brings us to the point of how do we define something in terms of mathematics? And the way 2 is defined is it's defined by its location on the number line. We're all familiar, Delaney, there you go, 2 units from 0. Exactly. You're talking about where it is located on the number line. So we all know 0 to be kind of the center of that number line, and 2 means you take 2 unit steps away. So now we say, well, how do we define 3? Well, 3 is 1 further than 2. And every number is defined relative to each other on the number line. So when we're talking about definitions in calculus, whether it's tonight or anytime throughout the year, what we're really asking is, do we know where it lives on the number line? If you can point to it on a number line, that means it's defined. Okay, so every stream that you're in contact with me, that is where we're going. We're going to say that defined means we can point to it on a number line. Now, conversely, if that's what defined means, what does it mean to be undefined? Well, exactly. It means we can't point to it on the number line. So these are 2 general ideas that I want you to keep in mind as we go through our calculus courses throughout the year. Anytime we're talking about defined, it means, hey, we know exactly where it lives on that number line. And when it's undefined, we have this question about where it should go. So from here, what I'd like to do with you guys is eventually get back to the idea of what is a limit, but I actually want to just jump to a couple of examples. So to do that, I need to switch over. So if you just give me a second. Give me one moment while I pull up my tablet. Okay. I'm hoping everyone now sees my tablet up. So what I want to do is I want to look at that first problem we just talked about. And that was, what is the limit of x squared as x approaches 3? So tonight's lesson is really all about using graphs to try to understand limits. So what most of us did is we looked at this graph and we said, okay, we want to go to x equals 3. That means we're approaching this value right here. So when we look and go, well, when x equals 3, we're asking, what is our output? And that's the equivalent of just plugging 3 in, and 3 squared would be 9. Simple, not a big deal. This graph's very consistent. It's very smooth. No problems there. What happens, though, when the graph is not so consistent? So now we look at this example. And again, the question is still, what's the limit of f of x as x approaches 3? But this graph has a little bit more to it because it's not as smooth and it's broken. So when we look at 3, there are a couple things I want you to think about. And I see a lot of you guys are answering, which is great, and you're coming up with does not exist. I got an answer of 2. Let's think about how we approach this so that we know how to answer a limit question. And one thing I meant to say earlier, at any point in time, you have any questions at all, just pop them into the chat. I'll be able to take a look at it. We got a fairly small group tonight, so I want to help you guys out as individually as I can. Anything you have for a question, please be sure to let me know. So now, here is what I want to look at. We want to go to the x value of 3 in this problem. And when we go to 3, well, that is exactly where we have the break in this function. Okay? We have an open circle, we have a closed circle. Open circle, we all know that means not included. Closed circle means included. So there are really 2 y values in play here. So when I was working with my kids today and I asked this question, and keep in mind that they'd never seen a limit before, and I asked, what are the different answers that we could? Well, pretend we gave 3. Someone gave me a pretend potential answer of between 3 and 5. Okay, all the numbers in between. And since they'd never seen a limit before, and how do we take a limit? And this is where you have to understand the most important part of limits. And I see in the chat some of you are already making reference to it. The idea of a limit is which direction are you coming from? So what I always tell my students is when you're taking a limit, cover up the actual value. And you can see in this new graphic what I've done is I've covered the 3 up completely. So students don't know which one's filled in, you don't know which one's the open circle. And the idea is to pretend that you are walking along this function and you are approaching 3. So I'm going to be moving this way. Likewise, we just as easily could have been walking along the function from the other direction. So if we're coming from one side, if we're coming from the left, we're going to end up here at this value, and our left answer is going to be 5. But if we're coming from the other side, we're going to end up at this value, and our right-hand value looks like it would be about 2. So now you've got these 2 different answers. How do you decide which is the correct answer? Well, I want to remind you what happened back with the parabola. If we go back to this one and we do the exact same idea, okay? If we had covered that spot up and then we had walked in both directions approaching there, coming from the left, our answer was going to be that value of 9. And coming from the right, our answer is going to be the value of 9. It's the same value. This one's pretty simple. Both sides agree. There's no confusion whatsoever. 9 was the answer. Back to our current one, on the left side, we're getting 5. On the right side, we're getting 2. So what that means is you got to make a decision, but the problem is there's no reason to choose one over the other. Once this is covered up, they both seem equally valid. So now you want to try to answer with both, but remember what our definition of defined means. It means we can point to it one place on the number line. And this is kind of giving us this idea there's 2 places that are right. Because of that, as some of you have already noticed and commented on, this answer is actually considered to be undefined. Okay, so what we need to do now is we need to go and mathematically talk about how to write this and how do we do this when these problems get a little more complicated. So I'm going to go back and I'm going to switch back to my presentation so we can look at some of the notation on this. So earlier I said we're going to talk about the definition of the limit. I wanted to share those a couple of examples to kind of say a groundwork of where we're at. And now here's where we're looking, okay? This is our definition of a limit. Now, what this means or how we read this is the limit of f of x as x approaches some number, and since it could be any number in the problem, we're just going to call that a. That a just stands for the number we're approaching. So in the last example, it would have been 3, but it's going to change from one example to the next. So again, the limit as x approaches 3. Now you'll notice up in the exponent area, we've got a minus sign on that a. Well, when you think about the graphs we just looked at, we talked about coming from the left and we talked about coming from the right. Most everyone who's familiar with the XY axis, the Cartesian coordinate system, is going to know that we consider the left side to be the negative side and the right side to be the positive side. So when we write negative up in that exponent area, what we're saying is we're approaching it from the left side. And we're going to look at an example of that in just a second, but that's how we read it. So again, that first part says the limit of f of x as x approaches our value a from the left. The other limit is the limit of f of x as x approaches a from the right. And we've got a plus up there doing the same job as the minus, but this time because it's positive, we're saying that we're coming from the right. So to define a limit, we have to look at both of these 2 things individually. If we can get them equal, if they end up being the exact same thing, like in our first example, that is the answer to our limit. That's going to be it. So in this case, if the left side limit, the limit of f of x as x approaches a from the left, is equal to the limit of f of x as x approaches a to the right, and they both equal the same number, in this case we're calling it L, we define that limit to be that number L that we get. And I realize there's a lot of notation here. We're going to go and we're going to look at a specific example. We're going to put this all in context for you. But again, if the left side and the right side agree, we can now talk about the overall limit. And notice this time it says limit as x approaches a, no positive, no negative. We're saying it doesn't matter which side you come from. You're going to get the same result whether you come from the left or the right. And that result is the same as the two individual sides. So again, a lot of notation in this. Let's go and let's take a look at how this actually plays out when we see it in an example. So let me switch back to my tablet. And let's pull up a new example on the tablet. So, the right place. All right. Can everyone see my tablet okay? It looks a little smaller on my screen. Please give me some feedback. I want to make sure you can see what we're going to be doing. So does everyone see the tablet okay? I'm having a little bit of technical difficulties. Give me one moment. All right, we're going to try this. So if we've got a situation, again, where we've got a graph, and it's looking like this, and in this case, we're taking the limit as, let's say we go to 5. And our graph is coming up this direction, open circle on the top. Let's put that at, let's say, 7. And then we've got a closed circle down here, and let's say we put that at -2. Okay? What's going to happen with this is that we've got to think about what is the limit of f of x as x approaches 5 from both sides. So there we have the left-hand limit being written down, and now we have the right-hand limit being written down. Now, one thing you're going to want to keep in mind, if you're doing this on the AP exam, you have to show both the left and the right to earn full credit. So the idea is to make sure you set this up, make sure it's clear. In that free response section, they're going to be looking for your work, and they're going to be looking for these two specific things. So in this one, as we approach 5 from the left, that means we're going to be up on the top, walking this way, and that's going to give us the value of 7. Okay? As we do the one from the right, we're going to be down on the bottom, walking this way, and that's going to give us that answer of -2. Now, before we were talking about what is the definition of the limit and what does it mean. I just want to write that down again because it's so important. A limit is defined if we can approach, and in this case we're talking 5, if we can approach from the left side of 5, and we can approach from the right side of 5, and we get equal answers. So in this case, our left approach was 7, our right approach is 5. Those certainly are not equal. Anytime you get a situation where they're not equal, that automatically means your limit is undefined. If I were on the AP exam and this was the question that was asked and I need to show my work, this right here is what they would be looking for. That's going to earn the full credit. That's going to give them give you the ability to earn all your points. Just one more real quick example. This one's a little simpler. If we're doing this one and we're talking about approaching 10 in this case, and we put that at -2, because this function is smooth, there's no breaks, there's no hiccups in it. If you ask what is the limit as x approaches 10 of f of x in this problem, I know it's a little simpler, but again, you got to show the work. You got to ask what's happening on the left side, what's happening on the right side. And on this one, you're going to get the same answer, -2 in both cases. And that means your limit on the left is equal to your limit on the right. As soon as you see these two numbers match, you can now start to talk about your overall limit, and it will always be equal to the answers you got from both sides that agreed. Okay, so what we want to do tonight is we want to look at some more examples, a little more complicated, but talk about how we can apply the left and the right-hand sides to get these answers. We're going to jump back. We're going to talk just a second about a few properties of limits, and then we're going to do some more examples. Okay, so properties of limits. All we're saying here is if you take the limit of one function as x goes to a constant, and that equals a number, and again, we're calling this one L in the first case, and then you take the limit of another function going to the same constant, and that would equal k in this case. Okay, so you know the results of these two individual limits. The properties of limits tell us we can start combining them. So once we know this, we can add some other factors to it. So in this case, you know, it looks very much like the limit, the first one, f of x as x approaches c. Well, all we've done is multiply it by a constant b. So all that means is the constant automatically gets translated into the answer. Before the answer was L, now the answer is going to be that same answer L, but we're going to multiply it by a factor of b. Another property of limits that we're going to look at is if you have two functions being added together, the answer is the limit of the individual functions. So in this problem, you don't have to take f of x and g of x and do it together. Break it up. Do the limit as x approaches c of f of x first, then do it as limit of g of x as x approaches c, find those individual answers, and then combine them the same way. So in my class, we kind of call this the common sense rule. We just go term by term, and that's the key in this one. It also works for multiplication. So if you can take the limit of the first function individually and the second function individually, the result will be the product of those two limits. Division is also going to work the same way as long as your denominator limit does not equal 0, because that would, of course, yield an undefined. But if you're ever taking the limit of a quotient, you can do the numerator separate than the denominator and then just use those two answers. And then the last one I want to talk about is if you're taking the limit of a function that's being raised to a power, you can kind of ignore the power to start with, find the limit. These limit properties translate pretty nicely the way we would expect. They're all kind of common sense kind of things. So what I'd like to do now is take a look and go back and look at a couple more examples that are the types of examples that you might see on the AP exam. I'm going to be honest with you, the first couple I did are kind of warm-up ones. The ones we're going to look at next, I think, are going to be much more like what you can expect to see when you get to that AP exam on May 5th this year. So let's take a look at this particular function. Okay, so I'm going to zoom in on a little bit so you can see it well. We're going to be using these two functions this evening. So this is our function f of x that's kind of being highlighted here. You can see that we've got a couple of breaks in it. You know, we've got some funny business going on right here. And we've got a horizontal vertical asymptote right there. That's going to cause some problems. We've also got the idea of just a random point right there where the function exists. And all these things are going to be on the graph, and we've got to know how to decipher them and know what's important and what's not important. So this is our f of x function. We're also going to be using this g of x function as well. Again, we've got some breaks over here. We've got another kind of jump or a whole discontinuity there with a point filled in. So all of these things are the types of functions we see with limits. Because to be honest with you, the smooth functions, they're straightforward. The types of functions they're going to test us on the AP exam are more of these kind of broken, jagged kind of functions that you're seeing right now. So the first question I want to ask, just keep it simple, we'll build up the level of difficulty. When we look at f of x, and we just ask this question, what is the limit as x approaches 0 of f of x? Okay, so again, we're just kind of focusing on that one. I can't stress to you guys enough. It's about coming from the left and coming from the right and making sure that they agree. I just told my students today, I don't ever want you to answer the overall limit until I see you guys show me what's happening on the one-side limits. So every single time you want to look at this by saying, okay, let's look at the left side, let's look at the right side, let's see what's happening. So for this particular example, as we approach 0 from the left, that's the same as me putting someone on my function right here and telling them to walk this way until they get to the x value of 0 and find out what the y value is. So as we're coming from the left on this one, as we approach 0, that appears to be going to this y value right here, -3. Now, this is where some people get a little mixed up, and this is why I chose to show you this problem. If you're approaching 0 from the right, you might think, well, I'm going to put my walker all the way over here, and as he starts walking, what's going to happen? Well, he's going to get hung up on that vertical asymptote. So you might be thinking, well, he's never going to get to 0. He's just going to keep going. Here's the idea. When you're talking about a limit and you're coming from the right, you're not coming from the far right. You're coming from the immediate right. What that means is we're trying to approach 0 from the right. There is no reason to start over here at 5 or 4 or 3. We want to start as close, especially when we've got a function like this that's broken. So my advice to you would be to go over here and start, and now start walking until this guy gets to the x value of 0 and figure out what the output is there. So as he does that, what we're going to see is we're going to get the answer -3 as well. And that's like the magic moment, because what we now know is the left side and the right side are the same. As soon as you show these are equal, you can now come over here and talk about the overall limit, and you're allowed to say that this limit will be the same as the other two. Okay, so again, just working with this function, getting you to see it. One thing I want to bring up, and this goes back to the notation before we jump into some of the more difficult problems this evening. I have a lot of students who will go and write down something like this in their work. It won't be their first step, but it'll be somewhere in their work. Okay, if you don't mind, just check on who's with me. What's wrong with this? Why does this make no sense? What's the problem that we run into with this type of notation? Okay, good. So we're getting people jumping right in, okay? There's no function. There's absolutely no way we can start to look and get an answer, because every limit, like I said before, it has 3 parts. And I just want to talk about this really, really quickly, okay? Here's the example I used in class today. If I walked up to you in the hallway and just came up to you out of nowhere and just looked at you and said, what's the limit? You would have no way of understanding what I'm talking about. All right. So the idea is you got to give all the different parts, all the different pieces. And to do that, we really need to go back to the limit definition real quickly. Now, I saw some of you guys had mentioned in the notes over there, I'm not saying left or right on this one. Again, this is an overall limit. We're okay with this. The question here is the following for you guys. We talked about the mathematical definition, and the mathematical definition of our limit is when we can come from the left side, we can come from the right side, and we can show those are the same. But what is a limit if you're just conversationally speaking about it? Like if you were talking to someone who didn't know math, what would you tell them a limit is? Okay, and And is really look for Can you guys hear me now? Am I back? All right, we're back in business. Sorry about that. All right, I'll give her my SOS message here. We'll come back. And we're talking again about how would you describe what a limit is in words? You know, if you were talking to someone who didn't have a lot of math background, what would you tell them if they asked you what a limit was? So that's kind of where I think I got cut off. I want to just pick up with that. And the idea, again, is going back to our guys coming from the left and the right, okay? Our guy here coming from the left, he's walking, he's following the path, and his job is simple: walk until his x value is 3, and then figure out what his y value is. But because it's a limit, we don't want to actually get to the value of 3. We want to stop just short of 3. So as he gets closer and closer to the x value 3, you can see his y values are getting closer and closer to 5. He's going 4.5, 4.9, probably 4.99, 4.999, and he's going to stop just short of getting to 3. And what he's done along the way is he's collected this data. He's gone 4.5, 4.9, 4.99, 4.999, and he's just short of 3. So now his job is to take this information and make a deduction as to what the y value will be at 3. He looks at it and says, okay, we're getting closer and closer to the value of 5. And that's his answer. And the key here is to understand that the limit never actually gets to the value of 3. It stops just short, and then you make a guess as to where you'll be. On the other side, this person's doing the same thing. They're coming to 3 from the right side, and they're coming from just below this value, so they're going to pass the value of 1 right here. Then they're going to go maybe 1.5, then they're going to go 1.7 as they keep moving closer and closer. Eventually 1.9, 1.99, and then something like 1.9999, and that's going to stop them just short of 3. Well, they've got to look at this data, and they've got to guess, where do I think I'll be once I get to 3? And they're going to say the answer is 2. And this is the way we found our answers of 2 and 5. So what's really important about this to understand is if you're talking to someone and they're asking you, what's the limit? What does it really mean? Well, here's the deal. It's nothing more than a guess. We're collecting data as we come from the left and as we come from the right, and then we're using that data to say, what do we think the answer will be when we actually get to the value we're approaching? Now, in the first example we did with x squared, it seemed more like we just plugged in and we found out. In these other examples, I hope you're starting to see that it's really important that we talk about coming from the left and the right, guessing them individually, and then seeing if they match. So here's what I would like to look at for our next example. And I hope this is going to be large enough for you guys to be able to see on your screens. But I've got a limit here as x approaches 2. And this time we've got a little bit of a composition of functions. We got x. So I want to give you guys just a moment to look at this on your own and just see what you think the answer will be. Okay, so I'll give you a few seconds. If you start getting some answers, pop some things up in the chat. How about I give you just a minute or two to see what you come up with? So if you can see that and it's going to work for you, just kind of give me a thumbs up, and then I'll give you a second to try to work this out. All right. We want to take this and we want to ask, what's the limit x approaches 2 from the left? And what's the limit as x approaches 2 from the right? And then we need to tackle these two things individually to find out. So first thing we're going to do is we're going to look at this and we're going to say, all right, as we approach 2 from the left, it's a composite function. We're going to start on the inside. We're going to start with g of x, and we're going to say, what's going on with g of x as we approach 2 from the left-hand side? So starting with our function g of x, and I'll just enlarge this so we can see it a little bit better. We're approaching 2 from the left-hand side. So here is the number 2. We want to approach it from the left-hand side. That means putting someone right here and walking this way. So as we walk this way, people are going to see the 2, and here's the little danger I was mentioning earlier, and it's going to come out really clear here. If we just plug 2 in, the actual output for this function is -1, okay? We do not want to use that value. The -1 value is a trap in this because the idea of a limit says we never get to 2. So again, to me, the idea that really is very helpful is to take and just kind of cover this up a little bit. And if you cover that up, now you don't know there's an open circle or a closed circle. Now you're just collecting your data and you're finding out what we're getting closer and closer and closer to. So as this guy walks his way getting closer and closer to 2, we all can kind of agree, I think, that, that his x value, where he's going to end up, is going to be right here. This is going to be it. This is where we're predicting he's going to end up. So what's happening is as we approach 2 from the left, g of x is approaching 1. But I want you to think about this for a second the following way. let's collect data. How is g of x approaching 1? Well, g of x is approaching 1 by coming from numbers higher than 1. Like right now, he's at the y value 2. And then he's going to go 1.7. And then he's going to go 1.5. And then he's going to go 1.1. And then eventually he's going to start going 1.01 and 1.0001. And when we look at this data, that leads us to that g of x is approaching 1. If we now go and do the exact same thing coming from the other side, okay, we're going to get a very similar result. He's walking closer and closer to 2 coming from the right-hand side, and his y values are getting closer and closer to 1, and they're following this exact same kind of number pattern where they're going from 2 to 1.7 to 1.5, working its way down to 1. So now what's happening is this line of data right here is kind of describing what g of x is doing as x goes to 2. So once we've got g of x down, we can now look at the composite function part. So now what's happening is we're saying that g of x is approaching 2 following, again, this data. So really g of x is approaching 2 from above, which really means the numbers 2, 1.7, 1.5 working its way down to 1. So when we go over to the other graph, now we know what the inside is doing. It's getting closer and closer to 1 from numbers greater than 1. Well, let's see what's going to happen when we approach 1 in this graph, because since the inside function is approaching 1, we're going to find out what's happening when f of 1 is being approached. Well, when we look at f of 1, we're kind of looking in this area right here, okay? And again, we've got this idea of if we cover this up, our walker coming from this direction might think the answer is 1. Our walker coming from this direction might think the answer is -2. And then there's that kind of sucker value right in the middle that says, oh, the actual value is -1. Well, which is the one we have to pay attention to? We've got to go back to our left and our right-hand sides. This one's very tricky, though, because what's happening is, regardless of coming from the left or the right in the inside function, g is following this pattern. So when we come from the left, we're going 2, 1.7, 1.5, 1.1, 1.01, 1.001. And when we're coming from the right, we're following the same thing. So what happens is both of these get mapped onto this path. Well, what that means is, as we come from the left, we're on this path, which gives us a y value of 1. And when we come from the right, it gets mapped onto the same value as well. Since our left side and our right side are equal, both of these are going to be 1. Okay? This is a very tricky question because when we hear left side and right side, we automatically assume that we're going to be walking from the left side and the right side. But because this is a composite function, that inside function actually causes us to walk the same direction on both sides on the outside function. So I hope that is clear for you guys because I'd like to go and look at one more example this evening. So the next one is this guy, okay? Again, f of x, g of x, same exact graphs. For those of you, just to be clear, the overall answer for that last function was 1, okay? That's what it should be. So when we go to the next one, you've got a new limit. This time it's a sum of 2 different limits. We've got kind of a shift going on with g of x. Now it's g of x minus 5. Again, I want to give you just a couple of minutes, think about it, and then I'll wait for you guys to start giving me either some answers or some questions, and we can talk about how to handle this one. So go right ahead, and I'll just give you a few moments to check that out. Had the question, do we use both graphs? We will need both graphs for this problem. While you guys are working on this, I'm going to start setting it up. Okay, so what I've done is I've set up a left-hand limit and a right-hand limit, but I've also instituted one of our properties of limits. We said earlier tonight that if we've got terms, a limit of terms, we can do the limit of each term individually. So I just want to set this up by looking at this as two separate problems in each case. So in the first one, as we approach one from the left, you can see I've broken it up f of x by itself for one limit, and then the limit of g of x minus 5 as x approaches 1 from the left for the other limit. F of x, as x approaches 1 from the left, we're going to get on this graph right here. And again, I'm just going to do this real quick because I find it very helpful. I want to cover that up, and then I just want to ask, what is happening as we get on here and we walk closer and closer to 1 from the left-hand side for f of x? Well, this function f of x, as he gets closer and closer, I think we can all agree on this one that he is going to end up at this value right here. And so that's going to be -2. Okay. Now, for the other one, the limit of the g of x minus 5, this one's a little trickier, okay, because we've got a shift going on. So the way I like to think of this is I like to say, well, if x is going to 1, that x minus 5 is really going to -4. All right, so I really think of this as kind of going to a -4. If x is going to 1, this is really going to a -4. So I'm approaching -4 from the left on this problem because of the shift. So when I go to g of x and I want to look at this one, all of a sudden I am relocated in the g of x, and I'm relocated here at the -4 value. Okay, that's where I end up. So we want to look at this, and we want to say, well, when x approaches 1, my inside's really approaching -4. X is approaching 1 from the left. That means my inside's approaching -4 from the left. -4 from the left means I'm putting someone walking along this way. And as he goes this way, this data, every point along the line, he's getting an output of 1. So when he makes his guess as to where he'll be right here, he's going to go with the value of 1. So I think we're okay. That's saying that when we add these two together, our answer is going to be -1. So for the left-hand limit on this one, we've got an answer of -1. We've got to try to do the exact same thing now from the right. So as we go to the right, what we're going to do is we're going to approach 1 from the right this time. And again, don't get hung up too far out. Get close to 1 on that f of x function from the right and just start walking along it. And as he walks along here, he's getting closer and closer and closer to the answer. That's going to be right here. So he's going to guess this answer is 1. And now the same idea on this one. Again, x is going to 1, so x minus 5 is really going to -4. Because x is going to 1 from the right, we're going to -4 from the right. Okay, so when we look at this one, we're asking what happens when we put our walker on our function here and they start walking closer and closer to an x value of -4. Well, we're going to guess that our answer is down right here at -2. So from here, what we've got is our first part has got an answer of 1. Our second part's got an answer of -2. We combine those. The limit coming from the right is -1. And now we check to see if the overall limit exists. The overall limit will always exist if the limit from the left is equal to the limit from the right. In this case, they're both equal to -1. That means our overall limit has the same value of -1. These last two limit problems that we gave you guys tonight, they are the most complicated types of graphical limits you're going to see. When we have two different functions and shifts especially, it really is a challenging type question. You're going to want to try to practice these. The last couple of years, the AP exam has shown problems like this in the multiple choice. So it's something you're really going to want to practice and get good at. And again, this is the idea of a graphical limit. So if you guys have any questions, feel free to pop them up. We're going to be wrapping up here real shortly, but I'd like to make sure that I address any questions you guys might have. I just kind of want to summarize the most important things you can remember about this evening. First of all, the definition of a limit. How do we know where that limit answer is? You can't do it unless you look at what is happening on the left what is happening on the right, and the only time it's going to work out is if these two things are equal. If they match, then what that tells us is that there is an overall limit we can talk about. No left, no right, it doesn't matter which way we approach, and that limit will have the exact same answer, okay? Always check the left and the right. The other thing I want to make clear about is always make sure you include all three parts of your notation, okay? If I just write LIM and nothing else, that's like me saying, yes. Hey, I have no, what do you want? Well, we are guessing f of x, okay? And as we know, f of x is just another way to say the y value or the output. So every limit we do, we are asking, what is the output? Can you guess the output? But because the function has an infinite number of outputs, we need a little more information. You need to narrow down where you want us to look. And that's this third part. Guess, the limit says guess. The f of x says the output. And the x approaches a tells us where it's happening. Leave any of these three parts out, it's going to be a recipe for disaster as you try to set up your limit and get the final answer. So, again, I'd just like to put it out to you guys. Any questions this evening that you'd like to put it up now? Could you explain how the answer is 1 for the second to last? I'm going to ask us to find the limit of f of g of x as it approaches 1. So you're talking about, let me go back to that one. This one, correct? Give me an okay if that's the one you want. Yep, okay. So again, we'll just go over this one. Let me just kind of start. The key to this one, and this is the tricky one. The key to this one is to understand when you look at the limit as x approaches 2 of g of x. When you look at this limit, that's this graph right here, you're going to agree that regardless of whether or not you come from the left or whether you come from the right, we're going to get this answer 1. Okay? I'm sorry, we're going to get the answer 1. But the key to understanding this problem is how we get the 1. How do they approach the 1? And in both cases, we're approaching 1 from numbers greater than 1. We're approaching 1 by going from 2 to 1.5 to 1.1 to 1.0001. Okay? So that's the key to understand how we're approaching this 1. From above, 2, and then working our way down to 1. What that means now is when you go and look at what happens with the outside part, what happens when we do the limit, actually let me write that over here, what happens when we do the limit as f, and I'm leaving this blank because the g of x is what's changing. This g of x, we're going to approach this, and again, I know it says that x goes to 2, but this was applied to the g of x. Now we have to take on what's the g of x doing. And the g of x is making us run through the numbers 2, 1.5, 1.1, and 1.0001. So again, if we look at what happens to this function as we follow this pattern of numbers, that means we're approaching 2 from this side right here. That's how we're approaching 2. So when we finally get down to make our guess, we've collected all these numbers and we're guessing our answer is 1. That was true for both coming from the left and the right, because g of x follows the same number pattern regardless if I'm coming from the left or the right. So again, even though I've got this left and right on the 2, what is g of x doing? G of x in both cases follows this progression. 2, 1.5, 1.1, working its way down to 1. So regardless of its left or right, since we follow this progression, in both cases, we're following the progression from above, following it from the numbers greater than 1, which means I'm coming this direction in both cases. So I hope that's a little bit clearer of an explanation on that one. I'll go on to another question. Why do we ignore discontinuity when approaching from the left and from the right? So Paul is asking this question, and if you mean, a situation like this guy, the asymptote, there's a big discontinuity there. Where are we approaching? And again, I'm trying to answer your question, but I need a little more clarification. If I was asking you on this f of x graph to approach 2 from the right, I don't start here because I would just keep going up all the way. I want to get as close to the input as possible. And I think that's the best answer I can give you. We don't necessarily, the discontinuity, it doesn't really make a difference if it's not as close to the input we're approaching as possible. So if I'm doing a limit in this problem and I'm approaching 2, I don't have to go far from 2. I can start here or here from the left and the right and still get the answer I need. Okay, follow-up. I mean with the part where you covered it up in blue. Why do we ignore the whole? Okay, I understand your question, so let's go back to that. So in this case, if we're talking about the whole, let's go and look at this function, because I think that's the one you're talking about, because that's where the whole is. It all comes down to, if we're approaching 2 from the left or the right, the idea of a limit is you never quite get there. The only reason we know there's a hole there is because we can see the exact situation at 2. If I'm taking a limit, the whole idea of a limit is I get closer and closer and closer and closer, but I stop just short of this. If I stop just short of it, I have no knowledge of whether it's a hole or if it's filled in. And to me, that's where the covering up comes in. Because when I cover it up, I won't get confused. I won't get fooled by it. As long as I see that hole, I think it's important. Once I cover it up, I don't know it's there anymore. It can't confuse me. So I hope I'm answering your question on that one. Do asymptotes affect the limit in any way? I think that's kind of related to what I was saying earlier. As long as the asymptote is not the point that I'm approaching, it really doesn't. Okay? When the asymptote is not the point we're approaching, it won't play a role. And again, I think I kind of said this earlier, but I'm going to just repeat it real quick. I'm going back to my f of x graph here. If I'm approaching 1 in this case, I just need to get close to 1. So I can actually start on the other side of the asymptote to begin with. The only time that vertical asymptote plays a role is if that is the actual value I was approaching. And just to clarify that, if I did ask, because this didn't come up tonight, but if we did ask this question, if we came over to this one and we said, what is the limit as x approaches 3 of f of x? Well, when we look at that one from the left, now I'm walking this way. So where am I ending up? I'm ending up in infinity. When I take the limit of f of x as x approaches 3, right? Well, again, I'm ending up at infinity. Because of f of x will be infinity. They match. And that's really what in some ways the definition of a vertical asymptote anyway, because it means that we're going to go up as high as we can as we approach that x value. So I hope that clarifies the question about asymptotes. Last comment, same thing with the dot and point limit. It's about getting close and not exactly it. So any other questions this evening? I'd like to thank you for joining me this evening. I hope that this made a lot of sense. It's a little hard without being able to see your faces, but it's great that I'm getting some of these questions back and this feedback. Tomorrow night, 8 o'clock, same time, same place, we're going to be doing algebraic limits, which will be incredibly useful on the AP exam. So if you got something out of it tonight, come back tomorrow night. We'll be doing algebraic limits. I'll be here again. Invite your friends. And I'd just like to remind you guys that every day we post on our social media the topics we'll be doing so you guys can know what's going on, not only in your AP Calculus class, but any of the other Calculus classes you're working on. So thank you so much for joining us, and I hope it was useful for you, and have a great evening.